Good morning, everybody, and welcome to our uh, ASPEN Net quantum tutorial series. Today we've got two speakers for you, Eric Chitambar from the University of Illinois Urbana-Champaign, and that will be followed up by Dr. Peter Bierhorst from the University of New Orleans. And today's focus is going to be on some of the applications of quantum networks. I also wanted to remind folks that coming up this Sunday, as part of the Quantum 2.0 conference, we're going to be having our town hall. And one of our plans is to take the information we gathered from this town hall and report back in one of these follow-up sessions for folks who can't come here. We're really trying to gather community input and feedback. So we're excited for that and hope to see as many of you as we can there this Sunday. So without further ado, I'm going to hand it over to Eric, who's going to take it away with our first set of talks on applications.
Okay, great. Thanks, Krister. It's a pleasure to talk here today with all of you. This is a two-part talk. So as Krister said, I'm going to speak first on quantum key distribution and quantum position verification, and then I'll hand it over to Peter. But the general theme of this is applications for quantum networks, specifically quantum communication and quantum computation. So we want to utilize the properties of quantum mechanics to realize secure information processing and secure communication. So I'm going to focus on just two applications here. There are many others, but I think these give you a sense of kind of the non-classical features that emerge when you're encoding with quantum information versus classical information. So let's start with this. We're going to talk about first quantum key distribution, which is probably the most mature quantum communication protocol. This has been around for, well, since the start of quantum information theory itself. And so I think it's a great place to start in our discussion of applications. So to begin with this, I want to talk about something that we're all very familiar with. And this is doing any sort of commerce on the internet or any sort of exchange of private information across the internet. And so if you look at your browser and you see when you type in a web address, maybe you see this little padlock icon appear somewhere on your browser. And so I wonder if you've ever asked yourself, like, what is going on? We see this and we feel like, okay, good. I see a padlock. Things are safe. So I can proceed with giving my life secrets away. But what's really happening here, right? So this should indicate some sort of privacy, some sort of protection of our information. And so the question is, how does your internet browser transmit private information over the internet? Okay. And currently at the heart of every secure communication protocol today is something which is known as public key encryption. Okay. So I'm going to give you kind of just like one way that this is done. In cartoon language, but it's capturing the essence of what's happening when you have some sort of communication across an untrusted network like the internet. There are bad agents on the internet who are trying to steal your information. So how do you communicate in that environment? And one way is using this public key encryption. And the general feature of public key encryption is that the security of it relies on some very hard mathematical problem. Okay. And it's the hardness of that problem is what's used to back the security. So one such problem is factoring prime numbers. Okay, let me show you a bit how this works. So consider this scenario here where you are a user on one end of the world and you're trying to communicate to your bank somewhere else, and you're going to use the internet. Now, again, as I said, the internet is a public network, so there are unsavory agents on the internet who may be trying to steal your bank information. So how could we possibly do this securely? Well, the way it works is, again, the algorithm is going to use some computationally hard problem. So the bank is going to use the difficulty in factoring numbers. So the bank on its end chooses two prime numbers, P1 and P2. Remember prime numbers, what that means is that the only divisors of these numbers are 1 and the number itself, right? You think about the factor trees back in when you first learned about multiplication. So the bank randomly chooses two prime numbers, and it uses these numbers to compute 3 new numbers. Okay, so it multiplies them together to get n. Then there's some other function, it call it a, that it's of the prime numbers, it outputs s, and then it also outputs another number k using some other function b. Okay, so 3 numbers, and the 2 prime numbers were the seeds. Okay, then what happens is that you can think of this A here as like a box, a security box, all right, hypothetically. And the K here, this is like the key to the box, okay? So the K is going to be held on the bank side, and what's sent over the internet then is the values N and S, okay? And we sometimes refer to this as public key, because this is what's being distributed over the internet publicly, all right? But you can conceptually think about this as like a box that's being delivered to you. Sort of like Amazon used to do this. When you would return something to Amazon, they would actually send you a physical box in the mail, and then you would, with prepaid postage and everything, you'd put your item back into it, and then you'd send it back to over UPS. This is the same idea. So there's some box that's sent to you, then you have your information M that you want to send back to the bank. So you put it in the box, you close the lid, and you send it back with some new form, that M prime. So this is like an encrypted form of M, which is using the N and the S. You send this back to the bank, and now the bank can unlock the box because it knows it has the key, K, right? So it applies some function, which then recovers the message M that you wanted to send. All right. This is the basic structure of how public key encryption works. So it looks pretty cool, but you can see that there's a vulnerability here, right? Everything that was used here to ensure the security depended on the choice of the prime numbers. If you look at how these functions were computed, we had N, which was just the product of the prime numbers. A, we applied some function to them to get S, and B as well. And so if you have a computer and you're able to, in fact, factor N, right, into its 2 prime factorizations, P1 and P2, then you've unlocked the whole scheme, right? You can determine S, you can determine K, and you've intercepted M prime, so then you could just run this function D and learn M, all your bank information. Okay, so this is a vulnerability of all public key encryption systems. But you may say, well, okay, fine, but factoring numbers is a hard problem, right? Are we really concerned about this? And to give you a sense of how hard this is, I mean, maybe you've never thought of it, but let's just try it in our heads here. So if I just gave you a number like 7,883, I ask you, is this a prime number? Well, maybe, right? You'd sit here and you could write it out and, again, do the factor trees like you did in grade school. And so the answer is yes for this number. If I gave you another one, 7,887, again, it's a challenging problem. This one, there's a trick here, actually. If you remember kind of this rule that if you add up all the digits and the digits are divisible, the sum is divisible by 3, then the whole number is divisible by 3 itself. So here we have 15 plus 15 is 30, which is divisible by 3. So this whole number is divisible by 3. So, okay, so that's not a prime number. But in general, there's no simple rules of thumbs like this. And even if you threw this at the best known algorithms, classical computing algorithms, if you put this into Mathematica or some other numerical solver, it would take the computers a long time to solve that as well. So as your number gets bigger and bigger, the computational time, how long it takes, also grows. And I'll give some exact numbers on the next slide. But here I'm just asking, is it prime? But go back, remember how we did the public key encryption. Not only did you need to decide if it was prime, you actually needed those prime factors. You needed P1 and P2. So that's an even harder problem than just deciding whether a given number is prime. Okay, so despite this being a seemingly hard computational problem, in 1994, some of you may have heard about this, which is known as Shor's algorithm. There was a mathematician, Peter Shor, who showed using a quantum computer that it's possible to factor numbers in a relatively short amount of time. Okay, and I want to put up a side-by-side comparison here. And if we put like ideal classical computers with ideal quantum computers, how fast can they actually factor numbers? And I love this comparison because it really shows the power of quantum computation. So right now on the classical side, if we gave a 193-digit number, I mean, we just looked at a 4-digit number, but now let's give it a 193-digit number, and you asked it to find its factors, it would take about 30 CPU years. So roughly what that means is you would just have a computer that's running for 30 years, okay? And then it could solve that. If you ran Shor's algorithm, ideally, it could factor that number in just 1/10 of a second. Okay, let's go higher. Let's put a 500-digit number now. And now it would take 10 to the 12 CPU years. And again, this is using the best classical algorithms that we currently know. All right. There may be better algorithms that we haven't discovered for our classical computer, but people have been working on this for a while. And this is what the best method we found. It would take 10 to the 12 CPU years. In comparison, if we did the same number on a quantum computer, it could be done in roughly 2 seconds. Now, what's going on here is that the reason that this gap is growing so large is that the time complexity for a classical computer is scaling exponentially in the size of our input. Whereas at the classical computer, it's only scaling polynomially. So if you think of like an exponential graph that's diverging, that goes as you move further away along the x-axis, it shoots up rapidly. Whereas a polynomial grows more gradually. So we're really seeing this difference between exponential scaling versus polynomial scaling. Okay, but now maybe some humbling news. The current factorization record on a classical computer is 232 digits. And so this is roughly 2,000 CPU years. And this was done by parallelization. So we didn't actually have a computer running for 2,000 years, but we had multiple computers running in parallel. On the other hand, if we think of with the current record, and this may be dated, we may be a slightly better, but the current quantum computing factorization record is a 3-digit number. Okay, so we're quite a ways, quite a ways off with our quantum computational power. But the main upshot here is that using Shor's algorithm, in principle, we could break public key encryption systems. Now, you could say, well, okay, is that really a problem? Because as I just said, we could only do a 3-digit number. That's the best where we are with a quantum computer. And we're still a ways off to achieving a full fault-tolerant computation, which is what you would need to really implement Shor's algorithm at scale. So this little roadmap here, I like this picture because it kind of depicts the steps that we need before we can reach fault-tolerant computation. We can run something like Shor's algorithm. And we're about here, maybe getting up to here a little bit, but we still do have a ways to go before we reach the highest platform there. So does that mean we just don't need to worry about this with our current crypto systems because we don't have a quantum computer that can break it? And I mean, this is debatable. Maybe not. Maybe we use a different classical encryption scheme, a so-called post-quantum encryption scheme. So maybe we don't need to worry too much. But on the other hand, you could say, well, fine, we don't have a quantum computer now, but there is a scenario where the current data that we have, like medical records, for instance, this is secure in some server, and it's encrypted in some server using the crypto systems of today. So there's some encryption that's placed on our sensitive data, like medical records. But imagine that those servers get stolen or someone downloads them. And then just stores them indefinitely. And then sometime in the future, when a quantum computer is built many years from now that can do Shor's algorithm and can break the encryption, or maybe a new classical algorithm is developed, or maybe there's some super quantum algorithm, or we uncover some new way to break the encryption system that we've used today, well, then all that encrypted information that is currently stored on those servers can be hacked and learned and decrypted sometime in the future. Okay, so we're always sort of vulnerable to this. Well, if our computational power got stronger, then the data that we have encrypted today could become decrypted in the future by nefarious agents and whatnot. All right. So there's a fundamental security problem here. And the good news is, while the Shor's algorithm is quantum computers that are hacking or breaking or decrypting the sensitive information, quantum also offers a solution. Okay, a remedy to the problem, and that is in the form of something what is known as quantum key distribution. All right, and it's an alternative method for secure communication over the internets or secure ways of encrypting information. So the way quantum key distribution works, here's like the high level picture of it, is that say you have two trusted parties, Alice and Bob, and they want to communicate to each other, and again, they're going to do it over some untrusted, we use the word channel, But you can think about this as like the internet. So here's this classical channel. This is like the internet, and the quantum channel. This would be like a quantum network where maybe you have someone who's trying to hack into the quantum network that we've learned about so far in these tutorials. Maybe there's bad agents on the quantum network that are intercepting quantum signals and are trying to learn some information about what's being sent. So again, we have this hostile environment, and we're trying to communicate privately between Alice and Bob over this hostile environment. And the way that QKD works is Alice and Bob, using this protocol that we'll look at on the next slide, they obtain what's known as a shared key. Okay. Now, what a shared key is it's a random string of bits in a random string of bits. So these are just zeros and ones, but they're perfectly matched. So if you look at these here, they're the exact same string. So if they're n bits long at each bit value, they're the same that Alice and Bob hold. And that's what's known as a shared key. And the key feature here is that Alice and Bob know the key, but Eve doesn't. Right? So somehow they're able to establish this key over a public channel without the eavesdropper learning the key at the end of the day, which is a pretty remarkable task if you think about it, right? Somehow this is an untrusted channel, and yet at the end of the day, Alice and Bob are able to get something private out of it. But what's the use of key? Why do we really care about having shared key? It enables something which is known as one-time pad communication. Okay, so let's look at what this is. Suppose Alice and Bob establish this key here. So now they both know all of the bit values in the right order. And now Alice actually wants to send Bob a message. So this is the message she wants to send, the strings of ones and zeros. This could be whatever. This could be what she wants for dinner, and she's going to encode it in a string of bits. So what Alice does is she uses the key, and she adds bitwise each of the bits with her message bits. Okay, so she's just going to add these together, and this gives her a new string here. Right, you see what I'm just doing? I'm just adding 0 and 1 is 1, 0, 0 is 0, 1, 1 is, this is mod 2, so this is 0. Okay, so she gets this new string, and now she sends this over the public channel to Bob. All right, and the eavesdropper can learn what this is. I mean, this is a public channel. Bob receives this number, and what does he do? He adds the key values back to it, and it just undoes the encryption. Undoes, we call this a padding. Undoes it, and then what Bob learns is exactly the message that Alice wanted to send him. Okay. And the key feature here is that the eavesdropper who learns this, from her perspective, it's just random noise, because this key is independent of the message Alice wants to send. So from Eve's perspective, it reveals no information whatsoever of the message that Alice is sending to Bob. So this is called one-time pad communication. Okay, and the idea is that using quantum mechanics, we can achieve a key that then can be used for one-time pad communication. And the protocol I'm just going to sketch here is what's known as the BB84 protocol, named after its inventors, Bennett and Broussard. 84. This is the year it was proposed, 1984. All right, and the way it works is it requires a quantum channel from Alice to Bob. So Alice needs to send a quantum state to Bob. And what she does is she chooses to send one of 4 possible states to Bob. Okay, so here are the 4 quantum states she sends. 0 and 1, this is the computational basis states, or we say the Z basis, or she might send plus or minus, which are superpositions of zeros and ones. We refer to this as the X basis. Okay, so this is like a Hadamard gate that rotates between the Z and the X basis. So she's going to choose one of these. She sends it over to Bob. We can conveniently write this 4 possible states she sends in terms of 2 bits, a basis bit and a key bit. So the basis is choosing between the Z and the X basis, and then the key is the 0, 1. That's which one of the two states she's sending among the 4. She sends this over to Bob. And now what Bob does is he also chooses a basis to measure in. So he's either going to measure in the Z or the X basis. And let's let his outcome be K prime. So K is the key encoding that Alice has, and K prime is Bob's outcome. And after she sends him the signal, then they communicate over the classical channel, and they announce their basis here, B and B prime. Remember, the B is the basis that Alice sends in, and B prime is the basis that Bob measures. And what happens is that if they they selected the same basis, if they randomly chose the same basis, then their K values will be the same. And all that's saying is that if Bob chooses the same basis that Alice encrypted in, then he can learn the 0, 1 information, whether it was 0, 1 or plus minus. He can learn exactly that value. Okay, and so then they use this shared K as the bits for their key. And they do this many, many times, and then they can generate a large key. So it seems like a very simple protocol, and you say, well, wait a minute, why is this secure? Well, the reason it's secure is because these 4 possible states that Alice is sending to Bob are non-orthogonal. And here, when I'm using in a very rigorous non-orthogonal sense of vectors that are not perpendicular. If we look at these guys, because the plus is a superposition of 0 and 1, and minus is a superposition of 0 and 1, they're non-orthogonal. Okay, and there's a fundamental no-go in quantum mechanics which says that any physical interaction that Eve tries to do on this channel will disturb at least one of these states. Okay, if you have a set of non-orthogonal states and you try to do some sort of interaction, some sort of hacking on Eve's end, it's going to disturb at least one of these because they're non-orthogonal. All right. In particular, what that means is Eve can't do something like this. She can't do this is like a photocopy, or we call it cloning. She can't take the state that Alice has sent and make 2 copies of it, keeping one for herself and sending one to Bob. So this is famously known as the no cloning theorem. But the main implication now is because of this disturbance, any attack that she tries to perform will have some non-zero probability of being detected on Bob's end, because you've introduced some disturbance. So Bob will be able to detect that disturbance on his end when he talks to Alice, when they do this transformation, this announcing at the end of the protocol. Okay, so this is really the heart of quantum key distribution, is the fact that any eavesdropper can be detected in principle. Now this is a high level argument for the security, and there's many assumptions going on here. And Peter, he's going to talk a bit about some of the other assumptions, like what if Eve has control of Bob's measurement device, or what if she has some sort of side channel that's going on here. There's many other attacks that Eve could possibly do. And when we generate practical quantum key distribution systems, we want to try to eliminate those as much as possible. I think Peter, in his talk, will talk a little bit about so-called device independence quantum key distribution, which means we don't trust our state preparation or our measurement devices, and yet we're still able to get key out or random numbers. All right, let me quickly move to the next application. Yeah, sorry, I want to just indicate this 12%. So this is roughly the threshold in which Eve will be detected. So she'll be detected with at least 12% if she's trying to do some sort of attack here. Let me move to the next half, and I want to be respectful of the time. So I'm going to just sketch out another application which looks similar to BB84 as far as the principle of what makes it secure. And this is known as position verification. So here is the setup here. So now we're a different framework. The goal is that we have 2 verifiers, two parties, these 2 oil rigs here. They're trying to ascertain whether some ship is a given distance away from the leftmost oil rig. Okay, so there's this. Imagine you're in the ocean, and this ship moves into this particular space in the ocean, and we don't necessarily trust the ship. The ship says, "Hey, I'm located a distance d from you," and maybe it's a cloudy day, so they can't put out their binoculars and actually check that the ship is there, or maybe it's so far away that optically you can't resolve the distance. How do you verify that this untrusted ship is actually where it claims to be? Well, one way you can do it is you can send some messages to the ship from these 2 oil rigs. And so let's say that the leftmost sends a bit value X, and the right one sends a bit value Y, and sends it to the prover such that it arrives at this location D at exactly the same time. So X and Y arrive simultaneously to the ship. Then the ship computes the XOR, just adds them together, and then sends it immediately back to the verifiers. Okay, so this sends Z is just the sum of it, and the verifiers will accept the prover only if they receive the correct addition Z at the right time, T1. Okay, Now, what happens? Let's imagine that the prover is not a distance D. Let's say, in fact, it's actually some bad guy that's closer to the oil rig than distance D. All right, so let's say halfway there. All right. Now, if we think about how this could work in time, so time is going up here, this pirate would intercept X at some point in time, at some point here in time. But remember, it needs to compute X plus Y, so it needs to receive both bits. And we know from relativity that messages can only propagate so fast. It's at the speed of light. So there will be some delay that this pirate must wait until it receives the Y message, and then it can compute Z, right? So it receives it here. But now there's a problem, because when the pirate tries to send Z Z to both of the verifiers, it will arrive after time T1. Okay, because it needed to wait longer to receive the Y information before it could compute Z. And so it's going to be send Z back too late for both verifiers to learn the right message. Okay, so that's like some intuition, but that's good news. But the bad news is that this thing can be hacked. And the way it works is, instead of having one pirate ship, you have two. And what happens is that these pirate ships are going to collude in a way where they both intercept the messages. So pirate ship intercepts X, the rightmost pirate ship intercepts Y, and they make a copy of this data, and then they broadcast it to their other partner. So the X is sent to the rightmost and Y is sent to the leftmost. And now, in the proper amount of time, they both have the X and the Y information. They can both compute Z, and they can send it back to the verifiers in the correct time. So the upshot here is that if you have colluding adversaries, they can spoof the verifiers into believing that someone is located at distance D, when in fact no one is whatsoever. And the way they do it is they just copy the messages that were sent. Okay. So this kind of undermines any sort of classical position verification scheme. But now you might say, but wait a minute. What did we see a couple slides ago when we were talking about QKD? We had the idea that this photocopying is not possible. We have a no cloning theorem. So maybe there's a way that we can do a quantum version of this, where we're going to use the no cloning theorem to make it successful. All right. And so the idea works like this. We have the leftmost verifiers chooses, again, one of these four non-orthogonal states that we saw before in the QKD protocol, sends it to the prover's location, and the other verifier sends the basis information. So it says either you measure in the Z basis or the X basis. And it's sent so that at the same time, the prover receives the quantum state and the basis information. And so then the prover knows which basis to measure in, measures in the correct basis, and then announces the encoded bit. So this X here is like K when we were doing the QKD. That's what that represents. It's like the shared key. Sends it back to the two verifiers, and they accept only if they receive it at the right time. All right. So the question is this secure? And as I said before, it fails against the classical attack because you can't do the same thing here due to the no cloning principle. All right. And so it turns out that this quantum position verification protocol is in fact secure. So it's secure if these adversaries, these guys here, don't share any other entanglement. So if they're just independent pirates, or maybe they're communicating with each other, but they're not quantum entangled themselves, then this no cloning argument is sufficient to prove that we can successfully verify the location of the ship. So QPV works in this setup if we assume that our adversaries aren't working together with entanglement between them. All right. So the bad news is that if they do have some entanglement, then that gives them a way to hack it. Okay, so there is a scheme where you can break the BB84 protocol that I just showed you if the adversaries have some shared entanglement among themselves. And it's actually a very interesting way that they hack it. So that's like kind of not so good news. But I would say that there's even better news, is that they're more sophisticated position verification protocols. Not the one that we just looked at, but there's more sophisticated versions where it requires the adversaries to share a lot of entanglement. And so you can, by increasing the size of the messages that are used in this position verification, the size of the tests, if there is a way to break it, it requires an amount of entanglement that scales in the size of the tests that are being performed. So I look at this as a potential new application that's distinct from QKD because we're not establishing key here, we're verifying a position. And we're using, similar to QKD, we're using the non-orthogonality of quantum states to ensure the security. So those are two of my favorites, secure communication applications. With that, I will turn it over to Peter to tell you a little bit more about some of the security and also the device-independent structures that emerge here.
Actually, just before we do that, Eric, so thanks for that overview. Is there any quick questions before we move on to Peter? Any questions for Eric on either quantum position verification or QKD or life in general? If not, we can also come back at the end to address any questions. Okay, well, thanks, Eric. We'll turn it over to Peter then.
Hello, everyone. Okay. Can people see my mouse cursor?
Yes.
Yes, I can see it.
Okay, great. All right. So thanks again, Eric. And I'll pick it up with this. So a lot of what Eric talked about was these quantum protocols and how you can hack them. And a big thread of what I'm going to talk about in my second half talk is the device-independent paradigm for making quantum protocols that are, very hard to hack, and specifically going back to the QKD thing, how this can circumvent some of the attacks that Eve can use on, compromising the measuring devices or the source devices, and then nothing specifically about position verification, but there are things that can be used there too. So device-independent quantum protocols rely crucially on a phenomenon known as Bell non-locality. So I'll just talk a quick bit about that. So this picture I stole from the 2022 Quantum Nobel Prize, or Bell's Theorem Nobel Prize, that was awarded for experimental demonstrations of Bell non-locality. And this little figure shows us what Bell non-locality is. So if you have two parties, Alice over here, Bob over here, and they measure some particles and they notice that there's this correlation that whenever Alice measures one and she sees white, that means that Bob is also going to see one that is black, or vice versa. If Alice had seen, the black one, then she would know that Bob had seen the white one. If you find yourself in a circumstance like this, you're going to assume that whatever was shooting these balls out to you just always had one black ball and one white ball and shot one way and one the other way. And then when you observe it, you're just revealing which one was sent to you. This is the hidden variable notion of how things should work. But quantum mechanics says that this pair of particles, if they're entangled, can exist in sort of a coordinated white-black superposition such that when Alice measures, that's the point at which the particle collapses into either white or black, and Bob's is perfectly coordinated to collapse at the exact same second of measurement. And so they discover at that moment not a pre-existing hidden variable, but the collapse of which one it went into. And it could have gone either way, and this was really like a random thing that happened right at the point of measurement. And so, let's abstract this a little bit, where we got Alice over here, Bob with a source in the middle. So Einstein, Podolsky, Rosen talked about experiments like this and said, surely the way things work must be the hidden variable way, that there's no instantaneous collapse, spooky action at a distance, that, when you're measuring these things, clearly there's some hidden variables where one of the particles is always white, the other was always black. But then Bell came along about 30 years later, and he showed that for certain experiments with multiple different measurements, it cannot be hidden variables that explain this. So if Alice is toggling between a couple different measurements and Bob is toggling between a few different measurements, you can come up with some quantum experiment where the quantum predictions do not admit any local hidden variable explanation. You can try to come up with this, well, this one was black and this one was white kind of explanation, but it just doesn't work. So this was tested many times in the 70s and 80s and 90s, and culminating in the 2015 loophole-free Bell test experiments. These are the citations for those. So this is a definitively demonstrated phenomenon that the Bell argument is correct, that these quantum experiments that John Bell spoke about can be realized in the lab, and there are no hidden variable explanations. And so the early experiments ended up winning the 2022 Nobel Prize. So those experiments had little loopholes and stuff, but they were very strong, but really the definitive experiments came around 2015. So this is well accepted now. So this leaves us in a scenario now where we have no local hidden variable explanation for the experiment. And what that means is, what do we make of these things where it's sort of existing in this superposition state, and then Alice's state, collapses right at the point of measurement and randomly chooses between two things, and then Bob's does? Well, if we don't want to admit non-local signaling, if Alice's particle isn't going to emit some faster than light signal to Bob's to create the correlation, then it turns out we have to accept that there's some degree of true randomness going on in the experiment. And as we learned from Eric's talk, randomness is a very useful thing in cryptography. So you'll remember the one-time pad where, Alice has some bit string she wants to send to Bob, in a cryptographic setting, forgetting about non-locality. Well, if she had some secret string of bits that she had and Bob had and no one else had, she could just mix her message with those bits, send it over a public channel, Bob could decode it, it would be perfectly secure. So that's, in a nutshell, why these Bell experiments are so interesting and evocative and useful for secure communication, is because randomness is a resource for these experiments that are not experiments, these protocols of cryptography. So let's talk then about applications to randomness of this bipartite non-locality where you have Alice and Bob and they're sharing a Bell state. So the first thing you can do is certify random numbers by the impossibility of faster than light signaling. And this is something that I did with the NIST Boulder group in 2018. We had a big project where we did a loophole-free Bell test and extracted that randomness. And remembering a couple slides ago, I said, if you rule out the hidden variable explanation, which a Bell test does, it rules that out, then you have to accept either signals faster than the speed of light to create the correlations you see in the experiment, or some unpredictable randomness. And so if you are comfortable saying that faster than light signaling is impossible, then you can be assured that you have these random numbers in the lab. So this is really a quite good source of random numbers. The randomness is assured by fundamental principles. Now, an interesting thing is if you go beyond this assumption of the prohibition on faster than light signaling, and you say, okay, not only do we rule out that faster than light signaling would be possible, not only do we reject that, but we also furthermore accept that quantum mechanics is a correct description of the universe, that if you have something that does a Bell non-locality violation, it has to actually be a quantum state. It can't be some super quantum thing. It has to be something that we can model with the postulates of quantum physics. This is a slightly stronger assumption, but one that we're all very comfortable making, because quantum mechanics is a well-accepted theory. If you introduce these quantum assumptions that say not only is faster than light signaling impossible, But anything that displays a Bell violation has to be a quantum state describable by quantum mechanics. Then you can get a faster random number generator, and you can do something called randomness expansion, which means you put in some random numbers, choose settings for Alice and Bob, and you get more out. And this series of works, takes this 2018 paper and is building stronger and stronger random number generation protocols. And very recently, we had a traceability result where a fully traceable random number generator, this is on the archive, it'll be published this year, 2025, shortly, where every aspect of the random number generation process can be sort of audited and certified. So a natural question for this is like, okay, that's all very fine and good. Why don't we just use pseudo-randomness if we have some need for random numbers? Or, maybe a standard quantum random number generator. So, if you're doing like sampling, right, and you're saying, okay, I want to, draw a random sample from the population and perform a political poll or something like that, it's perfectly fine to use a pseudo-random number generator for that, because you're not trying to hide a secret or anything. But pseudo-randomness, that would be something like, imagine the digits of pi. You take the next 10 digits of pi, and that gives you a effectively random string of 10 digits, and then you can use that to call a phone number or something. So that's effectively random, but it's not unpredictable. So if you have secret applications, like you're trying to do a passkey or cryptography or something, you can't use a pseudo-random key, because if someone knows that you're just using the digits of pi to create your passwords, well, then they also can compute the digits of pi. So you really want a real random number generator. So then, okay, why not use a standard quantum random number generator? Why not just measure a qubit in an unaligned basis, and that'll give you a 50-50 thing? Why go to all this trouble of having Alice and Bob be separate? And that gets into sort of the device-independent strength. And a couple reasons for that is that this is certifiably secret. If you run a random number generation protocol with an Alice and Bob separated, space-like separated experiment, and you violate a Bell inequality, then you're generating randomness. There's no way to violate a Bell inequality without generating randomness. This gives you a really strong trustability criterion. If you're a user, if you are just given some device that purportedly spits out quantum random numbers, well, you can put the Alice station over here and the Bob station over here and sort of time as these things are measuring. And if it's violating the Bell inequality, then it's generating random numbers. Whereas if you have something that's just, oh, well, we're generating photon and then we're measuring it, after it goes through a 50-50 beam splitter, to trust that, you would really have to open up the device, look at the laser, see that it actually is a 50-50 beam splitter, fully characterize it. So that's a nice strength of this. And no other random number generator could have something quite like that in terms of this trustability for the user. And it's also a fail-safe for the experimenter. If you are just creating a standard quantum random number generator, you don't know that maybe the interior things start to degrade and it's starting to introduce some cycle or something of non-randomness. But if you're violating the Bell inequality, that just tells you automatically, yes, you have this randomness. And then this last point I've put is something I haven't really mentioned a whole lot up to this point, is that, in the device-independent random number generation, Alice and Bob have multiple measurements. They have to sort of randomly toggle between them. And so part of running the protocol is using some randomness to choose the measurement settings. And that's fundamentally part of the Bell experiment. And so there's a little bit of a tautology here where, you need to use randomness to choose the measurement settings, and then it generates randomness. What do we make of that? It's almost like it's consuming the resource we're supposed to be creating. Well, the nice thing is you can sort of get private randomness, or not sort of, you can get private randomness from public randomness if you use something that's not such a secret source for your random numbers to choose the settings at Alice and Bob, provided that that random source is not in any way correlated with the states being measured. Then the output randomness is going to be private to any external user. So, you could be possibly using random numbers from some beacon and then running your own little Bell experiment using those beacon random numbers for the settings. And what do you get out? Well, you get out random numbers that are only known to you. So make a very good password. And then there's another protocol of expansion where if you sort of, and this was done in this 2021 paper, where you tweak the protocol a little bit and you figure out a way to use only a certain amount of random numbers to use for the settings, and you get more out from your Bell experiment. So if you had, this perfectly trusted, collection of random numbers that you felt really confident about, you could run this experiment and have a larger stream of random numbers at the end. Okay, so that's all fine and good. There's another more intriguing and communication relevant thing here is that, you've got Alice over here and Bob over here. And what we really want to do is not just create some password that, they know when they come back and share their data together. That's how these randomness generation experiments work. You want to sort of have a key that at the end of the experiment, you want Alice to know some numbers and Bob to know some numbers and no one else to know these numbers. And so these randomness protocols involve communication between Bob and Alice, where they share all of this information with each other to get something random. But in QKD, you want to, run the Bell experiment and end up with Alice has some secret random numbers, Bob has some secret random numbers. They're not at the same place, they're separated, and now they have this secure cryptographic resource. So Eric talked about the BB84 protocol. And how did that work? Well, forget about this source in the middle for the moment. You have Alice sends qubits to Bob, right? And it can be a 0 or 1, or it can be plus or minus. And then Bob measures his qubits in either the basis X or Z. And there are two key statements here. Alice prepares a qubit, and Bob measures these qubits, in the X or Z basis. Both of these assumptions are actually problematic when you go to a experimental implementation. It's not so easy to prepare a qubit and know that you prepared just a qubit. It involves like a laser, an attenuated laser. And possibly even more troublesome is the measuring of the qubit. And this is a real big problem. So if you have a photon detector and you're like, okay, well, if a photon comes in and it's polarized this way, it'll do this polarization measurement and that'll be all fine. If you just blast that photon detector with a flashlight, incoherent light, you'll set it off, and that's not a qubit coming in, that's just a big blast of light. And so these are attack modes that an eavesdropper can exploit, and they have done this where you run sort of a commercial QKD experiment, and you have these sort of auxiliary assumptions, basically on the order of, well, Eve's not blasting the, detector with a big blast of light that just forces it to go off no matter what. And then you can attack these protocols using these methods. And so here's the cool thing, is that if you're violating a Bell inequality, you can be assured of your desired state, or something close to it anyway. So if you're violating a Bell inequality, there's only certain types of quantum states that can do that. They're entangled states, and even a subset of those based on the quality of your Bell violation. This is a quantitative thing that can be measured, how much you're violating the Bell inequality. And the more you violate it, the more certain you are that you're within a certain distance of your desired quantum state. And the quantum states that have this, contain this secrecy, this qubit level secrecy, and there's no way to get around it. So device-independent quantum key distribution overcomes these hurdles. And there have been some demonstrations in 2022, some really good ones, Nadlinger et al. And Zhang et al. In Nature. These were proof of principle experiments. They were done over small distances, where one of them, Alice and Bob, were literally separated by 2 meters. And then the other one was a little further, maybe a few hundred meters. But in either case, when we're thinking about top secret communications, we're thinking about, hundreds of kilometers. That's kind of the distances that we care about. If someone's just in the office next door and you want to share something privately with them, you just go over there, walk over there, and talk to them with the door locked. So how do we get from these experiments to hundreds of kilometers? And that's where the quantum network comes in. And at ASPEN Net, we're building out this network, and we've got some great ideas for how to do quantum repeaters, which takes Bell experiments and sort of chains them together such that end to end you have a strong Bell violation that you might not have been able to get if you just had one source going directly to the extreme ends. And other things that we're working on, like heralds, which says, when you have a photon in the pipe, and quantum memories, all of which have been discussed in previous tutorials. All of these things are going to help take us from these 2022 protocols, these proof of principle protocols, covering small distances on the order of a few meters to longer distances on the order of kilometers. At least that's the hope. So that's how I segue this into quantum networks, because every slide I've had so far, I've had Alice and Bob, and the question is, well, where's the network? This is just a bipartite quantum experiment. And so, repeaters, that's the first level in which we would use this network to, build out these quantum information protocols at longer distances. But for the rest of my talk, maybe I'll take about 5 more minutes, 3, 4, 5 minutes. I want to talk about true three-party scenarios and device independence in this paradigm and what this might mean. So, let's say we have Alice and Bob and Charlie, and maybe they're sharing some quantum states, right? And maybe they share a classical resource that's shared between all three of them. That's often called shared local randomness. And so this is kind of like this just slapping together a whole bunch of bipartite links. It's a quantum network for sure, but it's not using a GHZ state. It's not using a three-way quantum resource. And we can ask the question, what correlations or probability distributions cannot be obtained from an underlying network of bipartite non-classical resources? These are these omega resources, even if we also allow the shared local randomness. We're going to ask this question because this question is basically saying, what can we do with genuine network resources that we couldn't do if we just had a bunch of bipartite experiments? And so there's a few variants of this question where we say, what sort of resources? We might even imagine that we allow those resources to be super quantum, like PR boxes. They can violate Bell's inequality more than quantum states. And can we still do things with three-way quantum states that we couldn't do even if we allow for super quantum resources? That's a little foundations of a question. A little bit more down to earth is, what kind of measurements are we considering here, like entangled measurements versus separate or separable measurements? So this first protocol I want to talk about, is going to be this sort of second idea, device-independent certification of effects. Let's imagine we have a scenario like this where Alice and Charlie and Bob and Charlie each share a Bell pair. So there's 2 Bell pairs. And Alice and Bob are always performing CHSH measurements. On setting Z equals 0, Charlie performs a Bell-basis entangled measurement. If he succeeds and observes his success signal, which happens with probability 1/4, he swaps a Bell pair to Alice and Bob, and then they can maximally violate the CHSH inequality. But if Charlie, instead of making this Bell basis measurement, just ignores the Bob photon and measures a basis aligned with one of Alice's CHSH measurements, this will lead to a perfect correlation with Alice when she measures that direction, which she's going to do, half the time. So she's doing a CHSH measurement. Half the time she's measuring this, half the time she's measuring this. Charlie will agree with her half the time. So it turns out that, no behavior can do this, can replicate the statistics of the experiment I just described using non-entangled measurements. It can be spoofed with a GHZ measurement. It can be spoofed with a GHZ state. That's a three-way entangled measurement. So in this sense, if we run this experiment and Charlie performs this entangled measurement, and they see the statistics, compatible with the experiment I've just described, there's no way to get those statistics if Charlie wasn't performing an entangled measurement. If he was just measuring the one source separately from the other source, they couldn't get the statistics. And so this is a device-independent certification of resources beyond simplest bipartite network resources. And it involves 3 parties, 2 measurement settings, and 2 outcomes for each measurement setting, described in my paper from 2023. And this is related to the device-independent certification of entangled measurements from Ramelow. They had a similar paper. Charlie has many more measurements and many more outcomes. This is sort of the simplest scenario where you can certify that you have entangled measurements. And then, what's the next level is, okay, suppose you allow entangled measurements. Is there anything that you can do with a GHZ state, which, replaces this SLR, which is classical stuff, replaces it with a genuinely tripartite entangled state? Is there anything you can do with a genuinely tripartite entangled state that you cannot do with the network that you're actually looking at here, which is bipartite entangled and shared local randomness? The answer is yes, there are things you can do, even allowing for entangled measurements. And so this, if you do that experiment that can only be done with a GHZ state, a 3-party entangled state, then you have device independently certified the presence of a genuine 3-way entangled state. And so the application here is to, testing and certifying hardware in a quantum network. So device independent in the sense that you're not actually trying to tomographically, analyze the state. You're just looking at the experiments of, you're just looking at the statistics of the experiment, and you just know that 3 separated parties cannot see these statistics unless they have a GHZ state. So that's the device independent character. So the future thoughts are, where do we go with this? Well, better optimal noise tolerance for certifying entangled measurements. The protocol I described earlier can be improved. We know that there's probably better, more noise tolerant versions where we can actually do an experimental test. But the thing I think is most intriguing is sort of a genuine multi-party protocol. It's already known that GHZ states can sort of outperform bipartite entangled states for certain things like conference key agreement, sort of a 3-way cryptography protocol. It'd be intriguing to sort of build this out and come up with sort of device-independent versions of these 3-way conference key protocols, things like that. And it's wide open field. So that's where I see this going. All right, so I will stop there right at 11 o'clock. And thank you for coming.
So thanks, Peter. So we have time for a few questions. So if folks have some questions they'd like to ask to either Peter or Eric, please feel free to do so. Juliet.
I had a question for Eric, and I guess I was wondering, what is the minus of doing the quantum position verification?
Eric, are you still on here with us?
He may have had to go. So if he's not speaking, he said something about the conference. Is he still here?
I don't see Eric on here. So yeah, Eric may not be. Yeah, so it looks like Eric's not here.
But maybe you could take this, Krister. I don't know.
So what was the question? Like, what are the downsides of position verification?
Yes, the quantum position verification. I understand that it provides new capabilities, but with every new capability, there are also things that are more difficult.
I think one of the things in the current schemes is on the classical side, you've got to really be, it's really this kind of time of flight. How long does it take to respond? So you need a network of very low latency communications, just classical communications to make this work, to really kind of localize and get this quantum advantage. So if you send your light through the fiber, that adds a lot of latency. So you got to be doing like really low latency, RF or some other kind of direct line of sight communication. Um, I think that's still something you want to develop anyway in a quantum network, because if you can have really fast classical responses, then that relieves some of the pressure on your quantum memories. So you don't need to store information quite as long because you can get your response back faster about whether operation succeeded. So I think it's still a capability you'd want to build, but I think that's one of the big, just from the classical side, that would be a big challenge.
So you made this comment about the latency and that RF might be better, but it will be slower. So I guess I'm still thinking about that, about whether, so I guess if you could go to sending electrical signals down a copper wire, if that's,
But you could do that. Why is RF free space broadcasting at the speed of light versus
oh,
traveling through a fiber cable at 2/3 the speed of light?
I see. So you're saying not use a optical fiber to do
Exactly.
latency. But then I guess you're limited with the free space links, you're limited as to how far you can go by obscurance, power, etc. Okay.
Yeah.
All right. Thank you.
Yeah, that's going to be a big challenge. Well, we're already a few minutes over, so what I'd recommend is if you have questions, you can email them to us. All the tutorials will be available and are available on our website, quantum-aspen.net, quantum-aspen.net, and so you can see them there. And we'll be reconvening in 2 weeks, and we'll be talking about how to develop a quantum workforce, right? So related to quantum networking. So thank you, everybody, and we'll see you in 2 weeks, and hopefully some of you
Yeah.
on Sunday at the town hall.
Yeah, or in 2 days. Yeah,
Or in 2 days. Okay.
3 days.
Take care.